Welcome to the next lecture of signals and systems. In the last lecture, we were solving some problems based on convolution. So, let us just start in the same direction. We'll solve one more problem and then we will move on to the discrete time convolution. Okay. So, the question states that you consider an LTI system and this signal xt given as 2e raised to the power minus 3t u of t minus 1. Okay. This represents the input output relationship, that is, if xt represents the input and it will give you the response as yt, and if this is the input, then the response will be minus 3 yt plus e raised to the power minus 2t ut. Okay, so the question is, determine the impulse response of this system. Determine the impulse response, that is st, of this system. Okay, so the system for which these conditions are shown to you, that is, this is the system, input output relationship is given, and for this particular input, that is dxt by dt, the output is this. So for this system you have to determine the impulse response. Okay, let us start its solution. You just first of all rewrite what is already given to you, that is xt is given as this signal. Okay, let me just okay, now define twice e raised to the power minus 3t u of t minus 1. Okay, so for obtaining this dxt by dt, obviously you have to differentiate both sides of this equation. So you just differentiate this. Okay, so differentiating both sides of this equation, what you will get? So on the left hand side it will be dxt over dt, and what will be on right hand side? So you just can simply differentiate it, minus 6 e raised to the power minus 3t u of t minus 1 plus twice e raised to the power minus 3t delta t minus 1. This represents the impulse signal, because you know that the derivative of this unit step will give you the impulse signal. So if you can just simplify it, you will get minus 3xt plus twice of e raised to the power minus 3t del of t minus 1. Okay, so what is this xt is given to you, you just can try to insert in this obtained expression. Okay, so you will be able to get this expression in terms of xt as this. Okay, now for this particular system, if this is given to you, that xt will give you yt. Similarly, if this is the input del t, it will give you the output as ht, which is called the impulse response. You already know this. And if this is the input, then the output will be twice of ht minus 1. These relationships can be written only if the given system is an LTI system. So it is already mentioned in the problem that the given system is an LTI system, that is, it is having both the properties of linearity and time invariance as well. Okay. Now this dxt over dt, which is obtained as minus 3xt plus twice of e raised to the power minus 3t del t minus 1. So this is already obtained in the previous you can say slide. So if this is the input, now this is already given to you in the problem that if this is the input dxt over dt, then your output will be this, okay, minus 3yt plus e raised to the power minus 2t ut. So you now see here that if this is your input, now what should be the output from here is minus 3yt plus twice of e raised to the power minus 3t h t minus 1. Okay, so in place of this x, obviously this yt will come, and in place of this impulse signal, the impulse response will come. So if this as a whole is your input signal, then this will represent the output for this particular system. Now from all this above information, if we can just compile the above steps, we will see that this minus 3yt plus twice of e raised to the power minus 3t h of t minus 1, that is this which we have just obtained here. So this should be equal to the expression which is given in the problem itself. That is, I will just go back to the previous slide. Here you can see that if this is the input dxt over dt, then this will be the output, minus 3yt plus e raised to the power minus twice t ut. Okay. So this will be just equated to it. This is t. So this will be just equated e raised to the power minus 2t ut. Okay. So now you just have to simplify this mathematical equation. Obviously this will be cancelled out from both the sides, and very easily you can simplify this equation. This is t minus 1 e raised to the power minus twice t ut h t minus 1 will be equal to 1 by 2 e raised to the power minus 3t and minus 2t ut, which can be further simplified to 1 by 2 e raised to the power t ut. Okay, so this is h t minus 1 equals to half e raised to the power t ut. So from this you can obtain the impulse response h t as 1 by 2 e raised to the power t plus 1 and ut plus 1. Okay, so in this equation you can just replace this t with t plus 1. So you will get the impulse response ht which is asked in the problem. So this will be the final answer. Okay, this is the final answer. Now we move on to the convolution for discrete time LTI systems. So we had seen that when we had calculated or evaluated the convolution in continuous time, we called it as the convolution integral. Okay, so when we discuss the convolution for discrete time system, or we try to find a mathematical, you can say, expression for the discrete time system. So we generally call this convolution as the convolution sum, okay, because this is for discrete time LTI systems. So you can also write in bracket that this will be for discrete time LTI systems, okay. So the procedure will be same as that we had done for the continuous time case, okay. So if I just go back to the previous unit where we had discussed the properties of the impulse signal. So from just you recall from there that the discrete time impulse signal, it has this property, okay. Now what is this? In this property we actually demonstrated, or we actually explained that the product of this xn and a time shifted impulse sequence, which is this, okay. So from here we can see that the multiplication of a signal, that is this signal, multiplication of this signal by a time shifted impulse, it will result in a time shifted impulse with the amplitude given by the value of signal at that time the impulse occurs, okay. So the component of xn at n equals to k, so xn at n equals to k is this xk n minus k. So I will just repeat the sentence which I just explained, that the multiplication of the signal by a time shifted impulse result in a time shifted impulse. You can see here that the time shifted impulse is coming here, but it is having the amplitude equal to this xk. So xk is nothing but the value of this xn at n equals to k, okay. So whatever this will be the actually the location of the impulse, and this will be the amplitude of the impulse xk, okay. So now this property, actually this particular property, it will help us to express this xn as in this form. I will just write it down here. So let us suppose x of minus 2 del n plus 2 plus x of minus 1 del n plus 1 delta n plus x1 delta n minus 1 plus x2 delta n minus 2, and so on. It can be written in this form, this general signal xn. So in the compact form it can be written as k equals to minus infinity to infinity xk delta n minus k, okay. So this particular property which we just discussed above, it actually help us to express this xn as the weighted sum of the time shifted impulses, okay. So for a linear system, if we know the system response to the impulse signal, that is delta n, then the system response to any arbitrary input can be obtained by summing the system response to the various impulse components. This thing we also discussed in the convolution case for continuous time systems. Okay, so if you just you know that this hn is the impulse response. Okay, and this is actually the response due to the impulse input delta n. Okay, so if this is the input, then this will be the response, and it is called the impulse response. So we generally use this notation in expressing the relationship between input and output for any particular system. That is the signal on the left hand side, it is the input, the signal on the right hand side, it is the output. So this is the general notation which you will find at most of the places. Okay, it is written like this. So this generally indicates the input output corresponding response of the system. Okay, so now using the superposition and time invariant property of this LTI systems, again we can just express the output as a linear combination of the system, linear combination of the responses of these systems to the shifted impulse signal. So if this delta n has the output of hn, then delta n minus k will have the output as hn minus k, and xk, delta n minus k will have the output as xk h n minus k. So if the input is this xn, which we represented in the previous slide as the compact form of the signal, which was represented by this summation xk delta n minus k. So if this is the input, then the output will be yn, and summation k equals to minus infinity to infinity. Let me write this more clearly. This is minus infinity to infinity xk h of n minus k. Okay, so you can see from here that we have obtained this system output yn to any arbitrary input xn in terms of the unit impulse response hn. Okay, so this can be written in this form: minus infinity to infinity xk h of n minus k, and this will be the, we just take it in a box. Okay, so this actually expression will be called as the convolution sum of the sequences xn and hn. Okay, so this will be called as the convolution sum, and you already know that the convolution is generally expressed by this symbol yn equals to xn convolution xn. So this thing we had already discussed in the convolution for continuous time case. So all the things are same here, only the difference is that here we have considered a discrete time system, whereas in the previous case the convolution was discussed for the continuous time system. So in the continuous time system the expression is called the convolution integral, whereas in the discrete time system the convolution is called the convolution sum. Okay, now let us see the procedure or the graphical method for the convolution sum. Okay, so again this method will be the same. uh, as we have seen for the convolution in continuous time case. Okay, so graphical method for this convolution sum. So if you just recall that in the convolution integral we discussed three different steps, that first you plot xn and hn, then you plot xk and xt and h of what you say, I think n minus k or n minus t, it was something like this. So these three steps will remain same here. Okay, the only thing will be that here we are discussing about the discrete time signals. So I will just quickly write down the three steps, that you first have to plot xk and hk. Okay, obviously you will plot this as a function of k. Now next you have to obtain h of n minus k. So in obtaining h n minus k from this hk, again you have to perform the intermediate operations, like first of all you have to perform this shifting, and then after shifting you have to perform the time reversal operation, or the time reflection you can also say it. So this will be same as h of n minus k. So this is how you will obtain h of n minus k waveform from this hk. Okay, and then you have to multiply xk and h of n minus k and add all the products to obtain yn, and add all products to obtain yn. Okay, so if you have seen the convolution problem that we discussed in previous lectures, you will very easily recall it, that this is the same three-step procedure which we discussed there. Okay, now we will very quickly move on to the problem for this convolution sum. Now let us say this is the signal xn equals to rect of n over 2n, or it can also be represented as this gate signal. So this is n over 2n, and this is equivalent to these values. Okay, so the question is that find the convolution sum of a rectangle signal xn with itself. Okay, or the second statement of this question can be that evaluate the convolution sum for a system with the input xn and the impulse response hn, which is given by u of n plus n minus u of n minus 1. Okay, so this can be the other statement, that either you convolute xn with itself or you convolute xn with this hn. Okay, now let us start the solution for it. So first of all you will write the convolution sum expression which is xn convolution hn, or it can be written as k equals to minus infinity to infinity xk h of n minus k. So in the first step, that is in step 1, okay, what you have to do, you have to write the equations and draw sketches for xn and hn. So this is simple, that if you, the expression of xn is already given to you in the problem, okay, you just rewrite this, and similarly you can also write the expression for hn. So this will be same as that of this xn, okay. So if you just plot this, since it's a discrete time signal, so obviously different samples will come here. So I will show it with a different color. Let us suppose that these are the different, you can say the samples, okay. So this represent the xn, so this will be minus n, this will be plus n up to 0, this is n, okay. And similarly if you represent hn, so hn will also be drawn in the same way as the mathematical expression is same. So this is hn minus n to n 0, okay, this is hn. Now this was the first step. Now in the second step, what you have to do, you have to write the equations and the draw sketches for xk and h of n minus k. So xk is simple, you can just replace the variable. So this will be this, and for obtaining hn minus k, obviously you have to apply that precedence rule or the shifting and the time reversal operation, which I just explained in the previous slide. And the expression of this can be written in this way, or you can also see from the waveform which you will draw, okay. So this will be, and this is less than equal to n plus n, okay. So again if you draw this, so xk will come as same like one sample here, okay. So this will be xk from minus n to n, the variable is changed, and now in plotting h of n minus k, so since there will be some shifting and time reversal operation, so obviously the waveform will be changed. So this you can see in the waveform of hk. So this signal will now be from n plus n, that is this point, and this point will be n minus n, okay, and obviously the variable is changed as k. Now in the third step you have to perform the summations to find the yn, that is the output for all the values of n. So obviously in this there will be different cases like we did in the convolution integral problems for continuous time case. So the first case can be if this n plus n is less than minus n, that means in terms of small n you can write it as n less than minus 2n. Okay, so if this is the case, then what you will see, we'll try to represent it with a waveform. Okay, if this is xk from minus n to n, and since this n plus n is less than this value of minus n, that means this h n minus k will be towards the left side of this signal. So if you will draw it with a different color, okay, so this will be n minus n, this point, and this point will be n plus n. Okay, and this signal, that is this, it is h of n minus k. So from here you can see that these two signals, they have no overlapping, they do not overlap the common, there is no common period between the two. So directly just you can write that yn, which is the summation k equals to minus infinity to infinity xk h of n minus k will be equal to 0. Okay, because there is no overlapping for these two signals. Okay, now come to the second case. Now in case 2, so again you have to draw the waveforms for xk and h of n minus k for this particular case. So you first draw it for xk. So this point will be minus n, this will be plus n. Okay, so this signal is xn, sorry, xk it will be, it is xk. Let me write it clearly, this is xk. Okay, now from this condition, that is this n plus n is in between this minus n and plus n. Okay, so that means that, let me draw it with a different color. So some portion will be common, this okay. So the waveform which is shown in this blue, it represents h of n minus k. Now from here, this point will be n minus n and this particular point which is in between minus n and n, that is this, it will represent n plus n, that is this point. Okay, and obviously this is 0. So from here you can see that now there is some common period in between these two signals. So now it is represented by this. So if you just do the summation for this common period, that is k is from minus n to n plus n, amplitude is always 1. So this will be, this is simple. You just have to add the sequences, whatever the number of sequences are there, you just have to add these two. So this will be the expression for this part. Okay, now move to the next case, that is case 3. Now in this case 3, this n minus n, now it will be in between minus n and n, and it can be represented in terms of this n also. Okay, so now again you have to draw the signals. So draw signals. Obviously xk will remain same because there is no change in xk, so this will be the xk. Now there will be change in h of n minus k, because now this n minus n is in between this minus n and plus n. So let us suppose now I will draw it. So this represents h of n minus k. Now from here you can see the common period between these two signals is this. You can also write the limits for this xk. This is minus n, this is plus n, whereas this is n plus n, and this point, this is n minus n. Okay, and obviously this is 0. So now you have to perform the summations for these parts, that is from k equals to n minus n up to n. Amplitude is always 1, so n minus n plus 1. So this will be twice of n minus n plus 1, and this is for this range of time, you can say. Okay, now there is one last case as well. What is this case? When this n minus n will be greater than n, or you can also write it in this way. These are same things. So you again just plot this. Xk will remain same. This is xk from minus n to n. Now it is given that this n minus n is greater than n. So now this signal hn will be drawn like this. Okay, so this is n minus n, that is the left limit, and the right limit will be this n plus n. This signal will be h of n minus k. So now from here you can see there is no overlapping between the signals, and no overlapping means the convolution for this part will be 0. So you just quickly write it down as this is equal to 0 for this time range. Okay. Now for all the cases you have to write all the expressions at one place. So this will be starting from the case 1, 2, 3 and then 4. And finally for case 4 there is 0. Okay, so this is the answer, you can say, for this problem. If you just draw this on an xy plane, you will get let me first draw this as straight line. Okay, so something like this. So a line will be here, then this, and similarly on this left part as well, it will be symmetric as the right hand waveform. Okay, so this waveform will look like this. It is resembling a triangular waveform. This will be 2n plus 1 this height, this will be 2n, this will be 2n, this will be minus 2n. Okay, this particular point. So this is a triangular signal, which is the result of this convolution operation. So this is the problems related to the discrete time convolutions. So with this much we stop today. Thank you very much.